Okay, welcome everyone. My name is Roman Schenscher. I'm the coordinator of this EBIO project. Today we will have our fourth and final webinar about the results and achievements in EBIO. That will focus on the process design, economics, and LCA of our process. Just a few minutes about the project itself. In EBIO, we developed electrochemical technologies to upgrade bioliquids. And there we worked on the characterization of the bioliquids, on new electrode materials. We screened them, we tested them in a lab and a pilot scale. And we also tested the upgraded bioliquids for co-processing in refineries. We had 3 webinars already, which you can find on the website. And today we finalize with the presentations of Matteo Gilardi and Julian Speckreise, focusing on the economics, process design, and LCA. So we start with Matteo. Matteo is a researcher at SINTEF, and he works mainly on process design of bio-based and renewable processes. And he will present today his results of the Techno-Economic and process design studies for the EBIO project. So Matteo, the floor is yours.
Thank you, Roman, for your kind introduction. Let me share my screen. Please let me know if you see it correctly. Can you see it in presenter's mode?
Yeah, now it works. Perfect.
Perfect. Thank you, Roman. So yes, I'm Matteo Gilardi. I'm since 2 years a research scientist in SINTEF, and my main expertise is modeling and process design applied to both bioprocesses and CO2 capture and utilization. It's really a pleasure to be here today to show you our results on process design and Techno-Economic assessments for the electrochemical upgrading of pyrolysis liquids, which is a key for topic that we developed within the EBIO EU-funded project. Let me start with a very brief introduction on the EBIO concept. As Roman introduced you before, we are targeting to replace conventional upgrading with electrochemical upgrading for liquefied feedstocks that are bio-based and industrially available. And in particular, we are targeting these for 2 specific feedstocks, which are the black liquor and the fast pyrolysis oil. More specifically, our project starts with a feedstock, which is actually wood or wood residues in alternatives. We have a thermochemical conversion that can be pyrolysis or kraft pulping, where we are producing our liquefied biomass, which is the black liquor or the pyrolysis oil. And then we enter in the core of the EBIO concept, which is the electrochemical upgrading that produces upgraded oil and also some side products, hydrogen and oxygen, that are really valuable either for downstream uses or for actually internal uses to perform the upgrading of the bio oil without depending on external utilities. And finally, the products are feed for the refining, where we actually target the production of industrial specifications for the fuels that can be used in the market, either as gasoline or as kerosene or as diesel. Before entering in the details of the work that we have done, I would like to emphasize and highlight which is the importance of pyrolysis oil upgrading step. Actually, in the oil that you get after the pyrolysis unit, you have high content of oxygen functionalities, which is mainly aldehydes and ketones, and also carboxylic acids. And these are known to result in a poor oil quality due to low stability, which turns out into coking problems. And this in turn results in a low percentage substitution allowed for these green and biofuels with respect to the conventional fuels for processing in refineries. If we want to improve this substitution percentage, we need to improve the quality of the oil. And this is what's typically done by means of this step, which is called upgrading. How does it work normally? It's a catalytic process which relies on supported noble metal catalyst on nickel. And another important point is that this conventional process requires high amounts of hydrogen at high pressures. And with high pressure, we mean something like 100 bars. And what we target in EBIO is actually to completely avoid this dependence on external hydrogen source in order to reduce the cost of the process and also reduce its environmental impact by developing a process which is essentially based just on renewable electricity as the energy source. And the specific aim of our assessment is actually to prepare the model for the process, optimize the process itself, and perform the economic assessment in order to investigate essentially how much we are saving or improving with respect to the conventional upgrading techniques. More in detail, we started developing the process flow sheet with the help of a process simulator. And this process flow sheet provides us the mass and the energy balance of the process. And then we use this as a basis to perform an integration of the single building blocks in an overall process concept design. And the main target is to optimize this process. Optimize means maximize its efficiency, which in other words means get as much biofuel product as possible and at the highest possible quality. But it also means provide an accurate way of recovering and separating the products in order to valorize also the side streams, which has a very important effect both from an environmental and an economic point of view. In addition, we also want to minimize as much as possible the unit operations that we need to target a limitation of the investment cost. And we also want to maximize its integration. So essentially, downgrade as much as possible how much we have to rely on external utilities. And in the end, we want to make a comparative techno-economic assessment to compare this innovative upgrading of bio-oil by electrochemical pathway with respect to the conventional route. In this slide, you can find an overview of the process that we have developed. We have pyrolytic oil as a feedstock, and we convey it to a mixer settler system where water is also added to induce a liquid-liquid demixing in the system. Two phases are formed and separated in a dedicated decanter. One phase is an oil-rich phase, and this is essentially already a product for us, so it's not what we are targeting to treat in this process. And on the other side, we are getting instead a water-rich phase that is what we want to treat in this process to recover as much as possible its valuable constituents. We send this water phase to a membrane column where we separate a solubilized lignin-rich phase and a sugar and acid solution. And these two solutions, they are conveyed to two separate electrochemical reactors to upgrade them. Solubilized lignin is conveyed to the reactor number 1, where we make an electrochemical oxidation that produces oxygenated lignin plus a list of organic compounds that I will show you more in detail in the next few slides. On the other hand, the sugar and acid-rich solution is conveyed to a second electrochemical reactor, where we perform a reduction using the hydrogen that is produced in the first reactor as a product. So we don't have to rely on external source, as you can see from the scheme here. And this reduction essentially produces sorbitol as main product. Moving to the details and methodology adopted for the modeling, due to the huge complexity that we have in the system, which basically means that we have to handle in theory hundreds or thousands of components, we have to adopt a simplifying approach that allows us to deal with this complexity within a process simulator. And what we adopt as an assumption is a lumped model where we identify the most relevant components to characterize the feedstock. And these lumped components have been divided into water-soluble and water-insoluble species to handle with the first step, which is the Mitzler-Settler, to separate the water phase from the oily phase. For simplicity and also due to lack of data availability, we had to simplify the models for the first two steps. So essentially the Mitzler-Settler as well as the membrane separator. And indeed, both steps have been modeled using a simplified compound splitter, where for simplicity, we assume 100% recovery efficiency for water and all the water-soluble species in the Mitzler-Settler system. And we assume that the efficiency of separation of the lignin fraction from the sugar and acid water solution in the membrane is also 100% efficient. For the electrochemical conversion of the solubilized lignin, which is the first chemical reactor, we have identified experimentally a list of components that are being forming, and this includes oxidizing lignin, some gases, and in particular, hydrogen plays a key role here since it will be exploited, as mentioned before, as a feedstock for the second reactor. And then we are producing the most relevant products, which are the organic compounds. And these include vanillin, vanillin acid, potentially also ethanol and methanol. We have identified some representative reactions to handle the mass balance within the simulator. And we are targeting how much of the products we are recovering, essentially, so how much organic compounds, how much hydrogen and lignin based on the data. And we simply tune the conversions to match these observations. For the second reactor, again, we identified that we have two main products, which are dextrose and sorbitol. Again, we don't need to add hydrogen because the hydrogen produced in the first reactor is enough to perform this second step. And this is very important, especially from an economic perspective, because we avoid the demand for hydrogen. The model of the reactor is an isothermal feeds conversion reactor, where we are operating at ambient temperature and ambient pressure, which is another difference from the conventional route, where instead you need high pressure, around 100 bar. What I would like to emphasize about this second reactor is actually the applications that are possible for the two products, dextrose and sorbitol. We know that dextrose finds relevant applications in the sweetener sector for baking products, but also, for example, in the medical sector for treatment purposes. On the other hand, sorbitol can be used to preserve the moisture, but also to add sweetness. On the other hand, it can also find application to support digestive and oral health. So again, different sectors that can both absorb in the market our two output products of the EBIO process. So now I've presented how we develop the single building blocks, so the single models that have been developed as plugins, essentially. And then we have combined these into a comprehensive process flow sheet. That's the one that you see here. And this has been implemented in Total Coffee, which is a license-free process simulator. Once we have the model ready, we use it to retrieve the mass and energy balance, and this is the basis for the economic assessment. Before proceeding with the investment cost evaluation, we need to size the units, of course. And this has been done in this simplified approach in EBIO, considering just the effective sizes for Mitzler-Settler, membrane, and reactors based on the available equipment that we have effectively used within the project. And then we have rescaled these if this was needed for the sake of modeling. Investment cost has been calculated using a fully traceable method because it entirely relies on correlations that are published in the literature and of course on the outcomes of the model itself in terms of the sizes of the units. It's a class 3 estimate, so it can have an uncertainty also of the range plus minus 30%. But this is sufficiently accurate for the sake of a preliminary feasibility study and comparison between different options. That's actually what we are targeting in this project. The total investment cost is the sum of three contributions. The most important is the equipment cost, that is function of the size of the unit, and this is calculated using correlations that are published. And then we have to actualize the cost to the present year, and this can be done using the chemical engineering plans cost index. And then we add these installation and indirect costs, which are function of the base equipment cost itself, multiplied by some factors, or the ones that you see here listed with F, whose values are simply retrieved from the literature. And here you can find a list just for the sake of knowledge of the values that we have used for these land factors. On the right-hand side of the table, you can find instead the breakdown of the investment cost. And this shows that, as expected, the electrochemical reactors are actually the key contributors in terms of investment cost. And this is expected because essentially of the large volumes that is required for these units. Moving to the estimation of the operating cost, we have adopted the methodology proposed by Tarton, which means that the operating cost is calculated as a function of the investment cost, operating labor, utilities, raw materials, and waste treatment cost. And here you can see the prices that have been used for raw materials and utilities. And for electricity, because this is, of course, the key factor here in the operating cost estimation, we have assumed a Norway-based scenario. So it's referred to Norway, and it's referred to fully renewable power, because as we said, we want to target a fully green electricity-driven process. Here's the result of the breakdown for the operating cost. It's actually noteworthy that electricity is definitely the key factor here, as you can see on the breakdown related to the different utilities and feedstock. If we look at the same results from just a slightly different perspective, so which is the operating cost associated to the 4 units operation that we have in the process, again is the second reactor, the one that is consuming the most. And again, this is due to the fact that great part of the electricity consumption holds there. And now let's move to the most interesting result, which is the cash flow of our project, of our innovative process. Essentially, the main outcome is that if we consider a lifetime of 30 years, at the current conditions, so current electricity price, current feedstock prices, and current product prices, the investment doesn't look very attractive, because as you can see from the blue curve here, we recover more or less the investment after 20 years, but then we don't go much higher in the last 10 years. So basically, we just recover the initial investment. There's no relevant money gain there. However, it's important to notice that if there's some slight variations in either the feedstock price or the product price, this can change a lot in terms of considerations on the cash flow. And indeed, you can see that both an increase of 5% in the product selling prices, a corresponding decrease of 5% in the feedstock prices, would result in a relevant actually increase in the cash flow. So this would make the process actually feasible at all. In addition, we also verified that it's important to perform a sensitivity analysis on the electricity cost, because as we said, this is the main driving force of the process here. And indeed, we verified that, for example, if we supposed to increase by 5% the electricity cost, again, we shift from this light blue curve here to the dark blue curve here. So the change is quite relevant. On the other hand, this would also mean that a 5% reduction in the electricity price would also make the process feasible, as we said before, for the feedstock and product prices scenario. On the other hand, we performed also sensitivity analysis on the effect of changing the equipment cost. But actually, we verified that this is not really relevant, because as you can see from the green curve here, even if we suppose to increase by 20% the equipment cost, then the cash flow is not really influenced. So the message here is that electricity, feedstock, and product prices are what really drives the economics towards a favorable or unfavorable outcome. In conclusion, we have performed successfully a process design and preliminary feasibility study for an innovative electrochemical-based pathways to upgrade the pyrolysis oil. We have to point out that the lack of experimental data made us or constricted us to make some simplifying assumptions that we did as conservative as possible, but this must be highlighted as a limitation because most of the models needed to be simplified or data driven without without being able to follow a rigorous approach. The main outcomes is that at the current status of feedstock, product, and electricity prices, the novel upgrading process looks expensive, so it's not associated with a relevant benefit in terms of cost reduction. And the reason for that is two reasons: the high electricity consumption that is required in the electrochemical reactors, and also the large volumes associated with these two reactors. However, if we look at the results from a different perspective, it's important to point out that we know already that the upgrading is not able to provide already fuels that are ready for the aviation and shipping markets, but is actually instead worth to be assessed as a way to produce intermediates for top processing refinery, and then in turn would feed the fuels for aviation and shipping. So it's just an intermediate step. It cannot provide already the product with the final specifications, but it helps towards to meet the standards which are required by the top processing refinery. And upgrading is anyway needed. So if we don't go for the electrochemical upgrading, we have to go for an alternative way, and actually the hydrotreatment is the main alternative option there. But the hydrotreatment, as mentioned before, requires external hydrogen. Not only external hydrogen, but also hydrogen at high pressure. So here it's important to point out that the external hydrogen means either higher environmental impact if we still stick to conventional gray hydrogen, or anyway very high cost if we want to replace this with a green hydrogen source, because it would mean a huge electricity consumption to generate green hydrogen. So no definitive answer on the profitability of the process, but actually it looks an interesting, promising alternative to provide an intermediate for processing the refinery to target as a final product different fuels for aviation and shipping. Thank you very much. I hope that this insight has been useful for you to understand what we have been doing in EBIO for the process design and economics. And I would be glad to take any questions if you have. Thank you for your attention.
Thank you, Matteo. We just need to mention that there is in the Zoom app in the bottom row, there is a button for question and answers. So please write your questions into that one. We still see the questions from the chat and we will answer them, but it's easier to answer them directly in the question and answer box. With this, we continue with our second speaker, which is Jürgen Spekreise from BTG. He is a researcher and consultant, mainly responsible for the life cycle assessment, sustainability analysis of all kinds of renewable processes. So Jürgen, the floor is yours.
Thank you. I think you should be able to see my screen and hear me now.
Yes.
Perfect. Thank you for the introduction. And indeed, I'll give a quick introduction about BTG myself as well. And then I'll discuss the environmental part of this technology. So the life cycle assessment on the electrochemical conversion of process oil. But first, very briefly, where I'm from. I'm from BTG, Biomass Technology Group. We're a small SME in the Netherlands. You can see all our employees on this picture on the top right. We started about nearly 40 years ago as a spin-off from University Twente. And we developed into two business units. On one hand, we have the consultancy and project development. This is the group where I'm from. And on the other hand, we have research and technology development, and here we're looking into further developing the pyrolysis technology. So that's also where we're known for, developing the pyrolysis of biomass. You've already heard a lot about it in the previous presentation. This technology was developed in-house by BTG, and we have two spin-off companies, BTG Bioliquids, who is marketing this technology, and even further BTG Next, which is another spin-off company that is marketing the production of fuels from pyrolysis oil. But as I mentioned, I'm from the consultancy side of BTG. We look, of course, broader than pyrolysis technology. So we do all sorts of topics around bioeconomy. And then you can think about project management, so due diligence studies, technical, financial feasibilities. We also do policy support to governments. Then I'm talking about market studies, public procurement, consumer perception, these type of topics. And then, of course, what I'm here to talk about is environmental assessments. So we do environmental assessments at different levels. We can do exploration studies, comparing different LCAs, different LCA results, and then up to full LCAs, and of course, the latest European methods, such as the SSBD framework. What makes us as a consultancy unique? So when you say consultancy, you can think of all different types of consultancy. We're a consultancy firm that really has a tailored approach. So we don't do off-the-shelf solutions. We really look at what is the specific question and then try to answer this question. We do this partially for private clients. Unfortunately, those are usually with NDAs, so it's difficult to show off some nice projects there. But we also do a lot of European projects. So I listed here only some of them. We even have more than these. Just to highlight you a little bit the different type of topics in the field. I will highlight on the right, you have tech for biowaste. Here we developed a database of different technologies that can convert biowaste into energy, fuels, or products, looking at pre-treatment, conversion, and post-treatment or downstream processing technologies, and trying to present them in an easy way. So you can check out that database yourself by looking up the Tech for Biowaste database. Another project on the left, you see Aligned, where we look at different LCA methodologies. So a lot of different sectors. You see the sectors listed below. It's a little bit small, but it says construction, pulp and paper, woodworking, textile, and bio-based chemicals. Looking at these different sectors, they tend to use different methods for LCAs, and that leads to different results and might even lead to unfair competition for biomass feedstocks. What we want to do in Aligned is what are actually science-based methodologies that you could use in different sectors to make a fair comparison between for the use of the biomass between the different sectors. So this is much more a project with a lot of universities involved who are really trying to translate the science into practice. Of course, today we're talking about EBIO. I will not discuss EBIO too much. I think it was already presented a lot in the previous presentations, but I do want to stop a little bit on life cycle assessment because it is a topic that's coming up more and more, and it's a very useful tool, but it's also a tool that is easily misunderstood. So a couple of slides on what is exactly a life cycle assessment. So life cycle assessment comes from the desire to know how green is a technology. So we develop something new, something that we want to save the world with, but is it actually green, or is it not as green as we think it is, or is it maybe even much better and more green than we think it is? So for that, we developed the lifecycle assessment tool, a methodology to calculate and quantify how sustainable something is. But there are different sub-questions to this question. So you can ask yourself, actually, I want to know which part of my value chain have the largest environmental impacts. So if I develop my value chain, what are the parts that I should focus on? You can also consider comparing your value chains to something else. So we're producing biofuels. How does it compare to other biofuels? Or how does it compare to fossil fuel? Sometimes you just want to know how green is your technology to simply qualify for certain subsidies. And then you have to follow the rather simplistic LCA calculations for subsidies. Or you can go to the other end and you make it more complex and you want to improve LCA methodologies and add more calculations to the system. So there's a lot of different ways you can set up an LCA, and because there's a lot of different questions you can ask about sustainability. This also leads to the next point. When you are reading LCA studies, I often meet people that are confused about different numbers. Try to understand what the reason was the LCA was set up, what are the questions they want to answer, and then try to focus on the conclusions and not so much the quantified numbers that roll out of an LCA. So that out of the way, we can do, of course, a full LCA. One of the advantages of an LCA is that it has certain ISO norms that you can follow. These ISO norms will tell you what kind of impacts you should follow. So you usually do a multi-criteria analysis, not just global warming potential, but you also look at other impacts such as land use, toxicity, etc. You follow an uncertainty analysis, a sensitivity analysis. So you check the assumptions that you made in your LCA, what kind of impact do they have on your conclusions? And you also calculate sort of an error margin to make sure that the differences you observe between your different results, are they significant or not? And then, of course, you need an external review to make sure that you actually follow these ISO norms. This is something we do often at BTG, something that is quite a lot of work. It's fun to do, but it is a lot of work. When we look at EBIO, actually we have a quite low TRL process. So it's very difficult to really pinpoint the exact value chain. We don't know yet where we're going to produce things. We don't even know yet how the technology will look like exactly at large scale. So therefore, we said it's maybe not too relevant to spend so much time and effort to exactly do this, this full LCA. So instead, we do a screening LCA. And in a screening LCA, what we try to get is with less time and effort, we get a quick indication on the sustainability. So we make some more rough estimations. We only look, for example, at the global warming potential, just to get a good idea of where we are sustainability-wise. Of course, this then comes with a higher uncertainty, but we already have a higher uncertainty since we're discussing a technology that is at a much lower TRL rather than a factory, for example, that has already been running for 10 years and can give you exact emission data. So now that we know that we want to do a screening LCA, we have to assess what is the goal and the scope of this LCA. The first goal is to get an assessment of the overall environment impact. So try to get a ballpark figure of what is the environment impact. So are we roughly going in the right direction, or are we getting a lot of emissions that we have not foreseen? A second point is to get environmental hotspots. One of the advantages of having a low TRL technology is that there's a lot of room for development. So of course, from a technical point of view, and you just saw it from economic point of view, it's good to know where to focus on. But also from an environmental point of view, maybe we can pinpoint what are the parts that we should take in consideration when we further develop the technology. The third is more of a free one that we get. What you often see with low TRL technologies is that people are really trying to optimize things, to tune things, and really in-depth focus on the technology. Doing an LCA at an early stage forces you to sort of take a step back and consider the entire value chain. So what is exactly, how does this technology fit in a value chain? What kind of feedstock are we actually talking about? What kind of products are we making? So doing this at an early stage helps to put your technology in perspective. So to look at this value chain, it's a more simplistic version. I use a bit more black boxes than what you've seen before, because you've already seen more in detail the pyrolysis and electrochemical conversion steps. We start with forestry residues. We do a pyrolysis that you've heard before. So high temperature, absence of oxygen. We get a oily looking liquid that we therefore call pyrolysis oil. We do an electrochemical conversion. And at the moment that I did this LCA, we said, let's take fuels as a likely outcome as a target product. So going from forestry residues via pyrolysis and electrochemical conversion, producing fuels. Now that we have this value chain, we need to have data of each point in the value chain. Of course, the pyrolysis, that's well known at BTG, it's the technology that we developed, so that's not a problem. The electrochemical conversion is developed within EBIO, so we could take data from the project, make some assumptions on scale up. So that was in place as well. And then all the other parts, so the parts that are marked in purple, you can see at the bottom we used EcoInvent. EcoInvent is a database that provides you background data for an LCA, so in terms of forestry residues, for example, but also all the arrows in between, their transportation steps. That's all data from EcoInvent. To give you an example, what kind of data we need for this LCA work, I took the pyrolysis because this is the most detailed. When I ask for data, people often think of mass and energy balance. So you get the wood chips going in and the amount of pyrolysis oil going out. If you're lucky, you also get the process steam and electricity going out. But as you can see, there's a lot more that you need to know if you want to fully consider all the impacts. So especially for a full LCA, you need to think of the land occupation of the factory. You need to think of the nitrogen that you need to purge the system, the lubricating oil that's used. So all these impacts we of course have at BTG. On the other hand, it's a high temperature process. So then of course you also have to consider the formation of nitrogen dioxide and the carbogenic or the biogenic carbon dioxide that is formed. There's some dust formed as well, some water that you use for cooling. So all these elements we take into consideration when we do a full LCA. Of course, the EBIO process is not at full scale yet. It's much more difficult to quantify all these impacts for the electrochemical conversion. So that's also why we do a screening LCA to estimate most of these numbers. So then immediately into the results. The first result that we got from the screening LCA, so I put in the entire model into the computer, and you get a number somewhere around 34 grams CO2 equivalent per megajoule fuel. So every result that I show is per megajoule fuel. And as you can see, by far the largest part is on the electrochemical conversion. That's the bottom part in red. There's a little bit coming from the pyrolysis, a small amount from the biomass harvesting, and then a small amount from hydrogen. The model that I used still used some hydrogen as an input. But by far largest part is electrochemical conversion, which was a bit of a surprise. So of course, then you look a bit deeper, where does this come from? And of course, this is then from the electricity source. And the reason why it's so big is that the EcoInvent unfortunately still uses a electricity mix from 2014. I put the value chain in the Netherlands, since BTG is based in the Netherlands. So it takes a Dutch electricity mix from 2014. If we replace this, so let's say that at the time that the EBIO is actually implemented at large scale, let's hope that at that time we have full electricity from wind. So this is the most optimistic scenario, I would say. There you can see that indeed it decreases significantly, and most of the impact of the electrochemical conversion has been removed. The truth is probably somewhere in between, but I expect it by the time that EBIO is implemented, it will be much closer to the electricity mix from wind. So to give you the ballpark figure that I promised, we're around 7 grams CO2 equivalent per megajoule fuel. Comparing this to conventional gasoline, I took a number from a publication of last year. They give a range from around 70 to 95 grams of CO2 equivalent per megajoule for conventional gasoline. So comparing that gives you a saving of about 90 to 93%. So that's a significant saving to current conventional gasoline. Of course, ideally, we would like to compare it to biofuels, to other competing biofuel methodologies, but that is very difficult when you have a simple screening LCA where you don't take in this comparison. Going through literature, it's quite a challenge. LCAs, as I mentioned at the beginning, there's different methods, different databases, different scopes. different ways you handle biogenic carbon, etc. So very challenging to compare. To give you example from the same publication, you can see that different types of feedstocks, for example, jatropha, rice husk, used cooking oil, they have quite a broad range. So some are even into negative, and some are up to 100 grams CO2 equivalents. So putting our number here in comparison, I don't think is very fair or tells us anything. Another way to approach is look at what kind of emission reduction the other biofuel options give. And then you get a range that is also quite broad, ranging roughly from 50 to 80% CO2 reductions. Giving our ballpark figure ends up about 90%. I don't want to make a hard comparison, but it is clear that we are in the right direction. So it is a promising technology that, based on environmental assessment, we can definitely develop further. So to conclude, we show a significant decrease in greenhouse gas emissions compared to fossil-based fuels, where we reach around 90%. The main hotspot that we identified is electricity production. It is very important that we have as clean electricity as possible for this electrochemical conversion from the environmental point of view. And comparing to other biofuel options, it's not really feasible, since we did not do that within the same LCA, because if you do it in your own LCA, then of course you can follow the same database, the same assumptions, etc. So that's a very difficult comparison to make, but the initial, let's say the initial views looks very promising. Of course, to stress out, this has significant limitations. This is a screening LCA, so we have large uncertainties. Of course, we made a lot of assumptions on the EBIO process, and we only looked at greenhouse gas emissions. We did not look at impacts from land use, impact from toxicity, eutrophication, etc. You probably heard the whole scope before, and this would be done in the next phase when the technology is more mature. Speaking of the technology, it's still at very low TRL. Further development of the technology is expected, so it will be further developed, further optimized, which will change significantly the mass and energy balances and also the emissions. And important to note, the value chain is far from fixed. So I took a value chain and placed it in the Netherlands, but of course at this stage it's we don't know yet where it will be implemented or in what time. So a lot of uncertainty still in the LCAs. However, initial results, I think, are very promising. And with that, I reached the end of my presentation, and thank you for your attention, and looking forward to see what questions you have in the chat.
Thank you, Julian. We have a few questions. Matteo is already busy answering them, but let's discuss them anyway. We start with Maya. She had two questions about the biomass itself. So maybe Julian, you can answer that. What type of biomass could be used? And
yeah.
Yes.
Yeah, essentially, for how the process is organized and built, essentially whatever kind of biomass that is worth valorizing via pyrolysis can be used. And this includes essentially whatever green waste as well as whatever wood type. On the other hand, there's also an alternative, which is coupling this process concept with the so-called integrated biorefining. So also thinking about what we have been doing in other projects, an idea could be that instead of using the entire biomass for this process, we actually split it, and we start by an enzymatic treatment where the portion of the biomass that can be solubilized is solubilized. And this is essentially cellulose and demicellulose. And then we can get products out of there, such as ethanol, that can be either a product itself or an intermediate to get something else out of it. And then in this case, we get a residue which is lignin rich, because lignin is the only metal which is not solubilized. And then we can pyrolyze lignin and take the process that we have described today just for a lignin rich feedstock, which will mean that the attention is basically on the lignin upgrading part instead of the sugar and acid part. So there's a way to actually tune this. we can use the process as it is with whatever pyrolysis process for whatever wood, if we use the entire feedstock, or we can think about an integrated biorefining. So we do an enzymatic solubilization, we valorize cellulose and demicellulose in one way, and then we use these roots just for the lignin. There's different options, but that's the concept.
Julian, just to add, so what would be the suitable biomass feedstocks for pyrolysis? What works, what doesn't work?
As Matteo mentioned, it's quite a broad scope. It helps to have uniform biomass as a feed for pyrolysis. Currently, on large scale, is mostly woody biomass, so sawdust, bark, this kind of materials. But we have tested successfully also other lignocellulosic biomass. But usually we focus on sort of pure form. So, for example, you can think of olive stones that are residues from olive pressing, corn stover, this type of material. So lignocellulosic rich biomass.
Yeah.
What doesn't work is usually material that has a lot of metals or ash content, as we call it, because it gives you a lot of ash at the end. So if you have biomass that is not collected carefully and a lot of sand comes into the system, that can give issues for the pyrolysis. But usually this is an issue of setting up your value chain well, making sure that the people who supply the feedstock understand these limitations, and then you can make it work.
What about food waste? Is that something that could work, or is it too complex?
Food waste, I only know sort of industrial food waste. So like I mentioned, the corn stover or the olive stones, these are examples. Actually, sort of post-consumer food waste, I think might be difficult since it has a lot of nitrogen in it, which gives you a very different pyrolysis profile. But I'm not sure if that is something that we have tested here as well.
Yeah,
And then we have
knowledge,
to talk to the RTD department.
Yeah, and to my knowledge, I would add that yes, as you mentioned, there's two important things to state, which is potentially the best biomass candidate. One is the side products or impurities content that can create a problem, and the other one is the relative ratio of lignin that we have. Because as I said before, if it's a biomass which is very poor in lignin, probably other pathways are more convenient, as I mentioned before. But whatever biomass that has quite a significant lignin content and does not contain huge amount of metals or other impurities, that's actually the target feedstock that has to be chosen for this kind of process.
Right, then let's move on. Does another route, Tan asks, does another route also require high pressure hydrogen for hydrotreatment? If so, how can it be integrated with the electrolysis process to ensure compatibility? So I can just maybe mention, if you do liquefaction of biomass and you produce all kinds of bioliquids and you want to turn them into a fuel, then you will always need hydrogen. So you need to remove your nasty chemical groups, and you need to increase your energy density. So hydrogen is always needed. Now, in this process, when you do electrochemical upgrading, you anyway produce as a side product also a lot of hydrogen gas, which then you can also use for the catalytic upgrading. And that's also described in the process design presented by Matteo. There was a question from Ahmad. Did you only try model oils, or have you tested pyrolysis oils as well? That I can also answer. We tested mainly pyrolysis liquids, but also black liquor from a pulp mill. And we try to limit actually our efforts in terms of model components because of the complexity of those bioliquids. So we try to use them actually from the beginning to the end. Yes. What else do we have? Compare your process to oxy-combustion of the forest residue, generate electricity and use it to run the EV. What do you think, Matteo? To combust certain parts of your biomass and then use that electricity do the bioliquid upgrading.
I mean, it's one of the I would say hundreds of options that we have to handle the biomass. It's difficult to say just based on the concept if it would be better or worse. I think it's just an alternative as many of the other ones. But I think that here what we want to do is to valorize all the waste that we have in a way which is not combusting, but actually targeting on the opposite, the recovery of all the constituents at the highest possible purity. So I don't know what can be better or worse. It's just that it's leading into slightly different directions. But what we are trying to do here is more to find an efficient method to recover and valorize all the constituents that we have instead of just generating a waste that we have to burn, essentially.
And in fact, at PTG, the pyrolysis process, the non-condensable vapors, they are actually combusted, and electricity is produced from those. So it's already a part of this scheme. Then we have Sneha asking, how does black liquor compare with pyrolysis oil in terms of process costs and emissions? Now, this exercise we did only for the pyrolysis case, because that was the case that we thought has the highest potential to be applied commercially, mainly because most of the pulp mills are already in operation, and it's rather unlikely that there will be another pulp mill produced or set up and installed in the near future. So this exercise of TA and LCA was only done for the pyrolysis liquids. Then what else do we have? Let's have a quick look. Matteo answered a few questions already. Yeah, the separation method after the first electrochemical reactor.
Yeah, essentially, as I presented in the slide there, we have done a dedicated experimental test to characterize which is the main components that we detect as products out of the first reactor. And they are essentially a great mix of organics, which are in the liquid phase. Then we have oxidated lignin, which is essentially a solid. And then we have some gases, especially hydrogen, with just minor traces of other things. So it's quite straightforward, the separation, because we can just flesh out the hydrogen very easily, then that filter to remove the solid, and what we get as a main product is already the organics, which are the main products of the first reactor. The recovered hydrogen, as I said, is separated by flashing, is conveyed to the second reactor. Solid lignin is a byproduct, and the liquid solution is the main product and is recovered at sufficiently high purity. There's no need for any specific treatment here. It's just quite easy separation because we have compounds present in different phases.
Right. Then Ali had a question about what co-processing we use for the intermediates. That one can I answer. Basically, we do both co-hydrotreatment and co-FCC. So what we do is we take the intermediates, we fractionate them by distillation into the heavy and the light fraction, and the light fraction is co-hydrotreated with VGA and what else was it? LCA, and the heavy fraction is run to a FCC together with VGA. And co-hydrotreatment tests were done by Tüpraş, the Turkish refinery, and the co-FCC tests were done by ITQ. There will be one deliverable which will be public that will summarize the efforts and the results of the co-processing experiments. So please have a look in some time at our Zenero community website. There you can download it. Okay, then that brings me, I think we have more or less all questions answered. That brings me to just mentioning to you that we have a website, we have a Zenodo community, and we have a YouTube channel. Please have a look. You will find now already quite some, but in the near future, a lot more information, deliverables, reports, publications for you to download. And the webinar we have now conducted has been recorded, and you will also find it on the website and on our YouTube channel. With that, I thank Jurien and Matteo for the presentations, and I thank all of you
Thank
for your
you,
attendance.
Rama, for inviting us.
And you will also find then on our website the answers to your questions that you have written in the chat. Thanks, everyone, and have a good day.
Thank you all. Bye-bye.
Thanks. Have a good day. Bye.